So I'm writing 2, 3 progression. They all are, the all will be in geometric in nature. You just have to tell that how they are geometric in nature and so on. So tell me, what do you see here in all these series? The ratio of any consecutive two number of this series is constant. And here, and it will be called R, represented as R. Here the R is 2. Here the R is 1 by 2. Here the R is 1 by 3. And here the R is again 2. We will keep the other denotation of progression from arithmetic progression, like A will denote first term, Tn will denote nth term, and Sn will denote sum of n terms since A, or starting from A. Starting from A. So in a very quick observation, you can just identify that if 3 is the first term and R is 2, the next term I am getting by multiplying R to the first term. Next term I am getting by multiplying 2 times R, which is R square in the next term. And so on. If I'll multiply, and if I want to get nth term, I'll multiply n minus 1 time R to the first term. So the general definition or general formula for nth term will be Tn is equal to A into R to the power n minus 1. Okay. So rest everything will be same as AP. Like, how do I identify that a particular number lies on this series or not? So although a very limited number will lie in this series, if you'll go ahead in this series, because it is going by multiplication 2, soon enough it will cross 3 digit and then 4 digit and then 5 digits. So if a term is, let's say, 192, and if somebody is asking that whether this term will lie on this series or not, so I know that I have been I will keep multiplying 2 to reach at 192. So if any term here I'm checking about 192, or any term which lie in group has been got by multiplying R into R into R into R any number of times, I don't know how much time, and it will give you 192. That means R into R into R will be 192 by 3. And if I'll divide that, I'll be getting 6, 4. And here R was 2. So 2 to the power x should be 64. If 64 can be represented as 2 to the power anything, then this term will lie on this series. whatever the series was. And if it is 2 to the power 6, so through general term definition, the 192 will be seventh term of GP. This is the same thing which I have talked about or talked in AP. We just have to care that here R is the common ratio, not the common difference. Next thing was summation of the series. So here we will not be deriving the summation formula of summation. Well, but I'll write it as sum of n term would be a to the power r to the power n minus 1, a into r to the power minus 1 divided by r minus 1. So let's say if I have a series like 2, 8, 32, 128, like this. And I want to find the formula, or sorry, I want to check that whether it is true for 4 terms or not. So Sn would be from this formula, my first term is 2, R is 4. You can just see that R is 4, common ratio. 4 to the power 4 minus 1 divided by 4 minus 1. Okay. So what I'll get here is 2 into 4 to the power 4 will be 16 into 16, 256, 255 divided by 3. And if I'll divide it 85, the sum I'll be getting as 170. And I can just check that. What will be the sum here? 2 plus 8 plus 32 plus 128. I can keep on adding this and I'll get 170. So this is the formula, but there is a very interesting fact here. In some case, you have seen or you may find that R is not greater than 1. R is less than 1. Like 32, 16, 8, 4, 2, 1. I'm just writing these 6 terms. And I want to calculate the sum of these 6 terms, which are in GP. So if I'll use the same formula as Sn is equal to a r to the power n minus 1 divided by r minus 1. So what we know here is that r is less than 1. So r to the power n will also be less than 1. And r will also be, so both of the terms will be, both of these two terms will be negative in nature. And negative negative will get cancelled. So to avoid that kind of that process or that cancellation of negative, I'm not trying to avoid it, just simplifying it. I will just multiply both denominator and numerator by minus 1 to get the formula as this. So here I will not have to deal with any negative term. I'll directly get the sum. So if we'll put here, the first term is 32, 1 minus 1 by 2 to the power 6 divided by 1 minus 1 by 2. So 32 into 1 minus 1 to the power 64 by 1 minus 1 by 2. Then I'll have 32 into 63 by 64 divided by 1 by 2. And it will be cancelled. The sum would be 63. And you can just add all these terms to get 63 also. Another interesting fact is, what if this series goes on till infinity? Like 32, 16, 8, 4, and you want to add this series plus 2 plus 1, 1 by 2, 1 by 4. I'll just divide every term by 2 and I will get the new term. And so on till infinite series. I'll call it infinite series. So if you want to calculate the sum, I'll use the same formula, but some formula will get simplified because of this infinity. So S infinity, if R is less than 1, again greater than 0, A divided by, sorry, A into 1 R to the power infinity divided by 1 minus R. And I know if it is less than 1, the fractional number, the infinite power of any fraction will give you 0 or near to 0. Like 1 by 2 to the power infinity is 1 by infinity, which is kind of 0. Similarly, 4 by 5 to the power infinity will also be 0. So all these less than 1 common ratio, if raised to the power infinity, it will be 0. And then 1 minus 0 will be 1. So this particular formula will get reduced to A divided by 1 minus R. So if you want to find the sum of this, it will be what? 32 divided by 1 minus 1 by 2. 32 divided by 2, sorry, 1 by 2, and you will get the sum as 64. So you can just, many times you'll get confused that every time a positive number is being added to this. So how come the summation is not infinity? But if like we were added and we added these all these to 63, and then I have 63 and a half. And every time, every number that we are adding, like 63 here, and next complete, let's say 64 is here. So this half is here, then 1/4 is here, then 1/4 is here, 1/8, then 1 by 16th is here. So with every new terms, I will be inside this only. So the total sum will be 64. So this is how you can visualize it. If you're not able to visualize, that doesn't matter. You just need to know this is the sum when R is less than 1, and if you want to find the sum of a series for infinite terms. So this will be your summation formula. Now, why it was important? They will not ask any such series, and they will not give you any such series. They will give you a situation where you might get or find a series like this. Like they may tell, or the question may tell, there is a square of side 18, side 8, sorry. And what you did, you connected all the midpoint of all the sides. Then you also get, again, you got a square. And then you kept on doing it till infinite times. Like this. And the question is, find the area of all such squares that you have got till infinity. And like you'll keep on going inside. And you'll keep on getting squares. Like this. So the first square will have an area of 64. And you know that the side of the second square will be 4 root 2. This is 4, this is 4, then this will be 4 root 2. So area of this square will be 4 root 2, square of 4 root 2, which is 32. which is half of the previous square. Then again, area of the next square will be half of the previous square. Area of next square will be half of the previous square. And this is how we'll go keep on going. So what we saw, the situation was of geometry, but it gave you a series which was GP, where R common ratio was less than 1. So the sum of this GP as infinity will be 64 divided by 1 minus 1 by 2, and which will give you 128. 128 square unit. It will be the answer. So similar situation you can find in compound interest or even in probability or many topic of quants. So you just need to remember this point and you need to solve the question which are in your seats. Uh, in other chapters, whenever it will come, we'll be revising it at the same time. ठीक है, ये हो गया हमारा